Hi, I'm Braden Walker. I'm a software engineer at Figma. Today I'm going to be talking about LiveGraph, a GraphQL-like system designed to make building real-time user interfaces effortless. So I'm going to be talking through a couple of things. So first of all, why LiveGraph, why it exists at all, and what problems it solves. Then about scaling up and the challenges that we ran into, and then a new architecture that we moved to recently and what it affords for us. So for some quick background, if you're not familiar with Figma, it's a platform for teams to build products together. Now, this is really important to us. We want people to be able to collaborate and work together because we think better things are built together. So let's talk through a few things. First up, why LiveGraph exists at all and what we needed it for. So real-time collaboration is really important to us. This is everywhere in the product. We want it to work the same way alone as it does together. We want collaboration to feel effortless and natural. We need this to permeate the entire product surface. So we don't want this just to be within files, but everywhere within the product so that it feels alive. And latency is noticeable in this environment because you're generally collaborating with people that you're actively talking to. You might be in a meeting together. And so we need the system to move at the same speed that human communication does. So this totally rules out technical solutions like polling. We could never keep up. So life before LiveGraph. The way this tended to work is that when a product engineer was building a new product surface, they would handwrite an endpoint on the back end to deliver all of the data that they needed to display on that surface. Then, in order to add real time, they would explicitly add publishes and subscribes through a pub subsystem. So there were channels of events, and the back end had to figure out what to publish and when to show to the clients. Now, this had all of the problems that you might expect. So for one, it's cumbersome at development time because it's extra work to do. And so that effort would sometimes get delayed, sometimes would move to a fast follow for a product. And so the product surfaces would generally feel alive, but sometimes they wouldn't. We also had problems with missed events. It was easy to forget to publish something or forget to subscribe, for the client or server to disagree about where a particular event was supposed to go. And it was really difficult to debug. When something went wrong, because the cause and effect were so separate, it was really difficult to figure out what happened. So enter LiveGraph to solve a lot of these problems. It gets its name and its inspiration and a lot of its general workings from the same place as GraphQL, and it works in a very similar way. So we have sort of three things that the product engineers interact with. So one is an object graph. These are the data types and their relationships with each other. Then we have GraphQL queries where the UI can ask for the data that it needs, which might traverse those relationships as necessary. And then, and here's where the magic comes in from LiveGraph, React hooks. So instead of just asking for the results of a query, you subscribe to the results. And as things change on the server, we magically deliver those updates down to the UI. The UI gets new state and re-renders automatically. So I'm going to talk through each one of these things a little bit. So the object graph, here's a tiny little slice of what the object graph looks like. So we have files. Files have several comments. Each comment has an author. The author is a user that has a name and a thumbnail URL. Comments also get reactions because people can leave behind thumbs up or smiley faces. And those in turn also have authors. So if we want to render a UI that looks like this thing on the right, where we have a comments pane that says, all of the contents of the comments, but also the users that posted them, their thumbnails, all of this sort of stuff, we have a GraphQL looking query on the left there that says, for this given file, give me all of the comments in it. For each comment, give me the message that created that. For the user that posted the comment, I need their name and their thumbnail URL. And I need all of the reactions underneath so that I can draw them on screen. And the way this actually looks in the UI code is we write React components that know how to render out UI. But the way they connect with LiveGraph is with this use subscription call. So this single line means fetch me the results of that query, but also keep it up to date. And so LiveGraph knows how to watch for the changes that that query might need to see and notifies the client, and the client knows to re-render with the new state. So this one line of code is all it takes to make this comments pane real time. As people are posting new comments or posting new reactions, it will automatically update. All right, so I'm going to talk about scaling up. First, in order to do that, we'll talk a little bit about how LiveGraph works, and then we'll come to some of the challenges that we ran into doing this. So at the most basic level, this is LiveGraph's architecture. So we have clients that are mostly web browsers talking to LiveGraph, the server. They keep open a persistent WebSocket connection, and they send over the queries that they want to subscribe to. Now, LiveGraph takes those GraphQL queries and breaks them into individual database queries to fetch the objects that are needed. It asks the database for the results of those queries, it caches the results in a query cache, and then we watch the replication stream from the database so we can see every mutation that's happening to all the data and mutate the query results as they change based on those mutations and notify the clients when they have changed. Now, I'm using query to talk about two different things. One is the GraphQL query, which is the traversal of the object graph that the product engineers write in the client, but these individual database queries are what I'm mostly going to be referring to for the rest of the talk when I talk about queries. Now, let's talk about what it takes to scale this thing up. And there are a few scaling dimensions to pay attention to. One is that more product surfaces are using LiveGraph as their backend, both because we're building new things and because we're converting existing things to use LiveGraph. The complexity of those surfaces increases over time because users use those features, right? As time goes on, we have folders with more and more files in them because users are using them. And then Figma itself is growing overall. So we're acquiring new users and we need to worry about that. All right, so let's talk about some challenges. And one of them is that as we're getting more traffic, we need to add more client machines, which means naturally we add more LiveGraph servers to keep up with them. Now this has a couple of problems. One of them is that we have to fan out all mutations to all LiveGraphs. We don't know which LiveGraph is interested in which parts of the database mutating, because LiveGraph itself is in charge of keeping track of that. So we have to send all mutations to everyone. Two, the caches are fragmented. So we have query caches that live inside each one of these nodes. And because Figma is inherently a collaborative product, right? You might be collaborating with somebody else on the same content, but you're probably talking to separate LiveGraph servers. And so you're not likely to hit a warm cache. And three, and perhaps most important, we have to fan in all of the mutations to a single LiveGraph machine, and it has to process all of them. Because we don't know which LiveGraphs are interested in what, each individual LiveGraph has to process mutations to all databases at Figma. And as we're scaling up, we're adding more databases, we're serving more writes, there are more mutations to process. So this is existential because eventually one machine won't be able to get through all of this. So this led us to trying to build a new architecture. So I'm going to talk through a couple of things on this point. The requirements that we needed to fulfill, an idea that seemed sort of obvious at first, but we ended up discarding for a few reasons, some observations we came to in doing that, and then the three-tier architecture that we ended up with and how it works. So the existential requirements, on top of everything that LiveGraph already needs to be, it's the surface that the product engineers interact with. Of course, we need to deliver things with low latency, but as we're scaling up, these are the things that we're worried about. One, we need to be able to consume sharded database mutations. So as we're adding more databases, we need to not have a single node processing all of the changes. We need to process only a slice of them at a time. Two, we need to centralize and share the cache. This means that we can get better bang for our buck out of fewer resources. And three, we need to be able to scale this thing out as traffic increases, as usage increases, as complexity increases. We need to be able to add more hardware without increasing the fan in or fan out along with the scale of Figma. All right, so let's talk about an idea for solving this problem. And we're revisiting this sort of architecture diagram here. So we have multiple database shards and they each deliver all of the mutations to both of the LiveGraphs here. Now, as we're scaling up, we're adding database shards. And you might think that because we're already sharding the databases, we may as well shard LiveGraph the same way. So we split the query cache out from LiveGraph and have each one mapped to a single database shard. Now, there are a couple of problems here. One is that we need LiveGraph to be intimately aware of the topology of the databases underneath, the placement of data across those shards. Two, we need to be able to execute queries both forwards and backwards, right, across many database shards. A single query might not be homed on a single database shard, which means we have to fan out to the query caches that own fragments of that data and then be able to merge those results together into final queries and have real-time changes flowing the other direction, updating those things through that execution engine. This is all really complicated. And three, most importantly, this would mean that we are rather intimately tied when the sharding changes. So we need to be part of the process by which we move data around among nodes at Figma. And this is already a relatively delicate operation that has a lot of steps to it, and we don't want LiveGraph to have to be that intertwined with that process. So we ended up discarding this idea. But we observed a few key things about the way the system works. One is that the query shapes are known basically ahead of time. Now, the actual queries done against LiveGraph are written down in source code. They're committed by the product engineers working with LiveGraph. And so they change at about a human scale. They change day to day. They don't change second to second. Two, the queries are mostly simple. So we already have this enforcement from LiveGraph that queries can't have things like joins or sub-expressions, anything like that. They're basically all straightforward select wheres. Sometimes the filter expressions get kind of gnarly, but in general, they're straightforward queries. And then three, reads are much more common than writes. So this is important because the previous system focused a lot on making mutations and applying them to query results very, very efficient. But we can actually afford to do something slightly suboptimal here in order to simplify the system, which we'll see in a second. All right, so this is a diagram of the three-tier architecture that we ended up landing on. It's not going to be immediately obvious how this leverages the observations that we just talked over and how it solves the problems that we went through. But I'm going to talk through each one of these components in a second, and we'll see how at the end it all comes together to solve those problems. But at a high level, this is the general concept. So the important thing is that we have caches in the middle. These are cache results of individual queries. So the cache keys are SQL queries, the cache results are rows. Then, in order to keep that cache up to date, we have invalidators that are responsible for consuming the stream of mutations from databases and then emitting the cache keys that need to be invalidated. And then we have front ends that sit on top, and these are in charge of taking GraphQL queries and expanding them into database queries. When it receives an end validation for a query to say that the results may be out of date, all it does is requery. So this helps us avoid the complicated query engine edge that LiveGraph might have gotten into. All right, let's go through each one of these things. So we'll talk about how we generate invalidations. This is important for how we are able to consume database mutations in a sharded way. So we have these shapes that are written into source, like the thing at the top there, right? This is the file shape, which it fetches information about a particular file given its ID. So in a shape, all of the arguments are templated out. And an actual query is a shape plus the arguments that go into the query. So the mutations that we consume from the database look like this thing just below the shape, where we have a pre-state and a post-state. We get to see the state of a row before the mutation and then what the row looked like after the mutation. So this particular mutation is a rename, right? Someone changed the name of this file. And so we have to figure out which query needs to be invalidated. Now, given the shape file, we can figure out that the one that needs to be invalidated is the one with the ID that is this file. This is rather straightforward. Here's a slightly more complicated case. So we have a query shape that is responsible for fetching the files in a particular folder. So the argument is the folder ID. We want to return all the files that are in that folder. If we have a mutation like this that changes which folder the file is in, right? This is a move from one folder to another. We need to invalidate both the query that fetched the contents of the folder that it used to be in, because we need to see it disappear from where it used to be, and invalidate the query for the folder that it is currently in, because we need to see it appear where it's going. And here's a slightly more complicated case. Now, this query fetches recent drafts. So we use it on a particular folder to fetch files that have been changed recently, say in the last 7 days. So when we get a mutation that changes the updated at of a particular file, we need to figure out which queries need to be invalidated. Now, it's obvious that we need to template in the folder ID that the file is in, but it's not clear what we need to template in for the updated at, right? Because any query that is looking for an updated at that's older than either of these timestamps might be invalidated by this. So what we do is we cheat and we invalidate all of them. It turns out that this is super effective in practice because, generally speaking, the rest of the query that we can template in is selective enough that the over-invalidations are not terribly expensive. And two, because mutations are not that common relative to reads, remember, we can afford to do extra requeries when the results of the query did not actually change. All right, so we've shown that the invalidator is capable of generating cache key invalidations from just a single row mutation, which means we can trivially shard the invalidators. We can have them each consume just from one database shard and generate cache key invalidations from just that shard. Now, this sort of sounds like something from the previous design that we ended up objecting to, but it's different in a fundamental way. Because the invalidators are just working on single row mutations and don't need to know any other state, they don't need to care where the data is actually homed. And so they don't need to participate in any sort of resharding process, moving data from one place to another. They just look at mutations and generate invalidations. So this means we're not actually intimately tied with the database shards. We need to know what shards there are, but not any information about what lives where. Now, it kind of looks like we've got the same fan-in problem, just one step deeper. So let's keep moving here. So we take the caches and we also shard them, but we shard them by a hash of the query. So we take the entire query, the shape plus its arguments, and we hash them together to figure out which cache node is responsible for a query. Now, when an invalidator generates a cache key invalidation, it can also hash that invalidation and send it directly to the cache that's interested in it. So even though we have the same number of arrows between the invalidator and the cache that we previously objected to, each one of these arrows is actually carrying much less data because it's only the stuff that we know the cache is already interested in. Now, in order to prevent the fan out of those queries where we had to invalidate all arguments, we actually template out the arguments that we can't invalidate directly. So in the case where we had that recent drafts shape and we can't template in the updated at invalidation time, we also route all of those queries to the same node. So we sub in a star and hash that to figure out which cache node to send it to, so that we only have to send the invalidation to one node, even though it might invalidate multiple queries that are living on that cache node. And the next step is adding front ends. So as we're scaling up, we're adding front ends to serve more user traffic. And in order to deal with this, we need a way of routing invalidations from caches to the front ends that are actually interested in them. And the thing that we use to do this are probabilistic filters. So these filters are allowed to say, for this query, is this front end interested in it? And sometimes it will answer yes, even if the front end isn't actually interested in it, but at a low rate. But they will never answer no if the front end actually is interested in them. But they have this advantage that they're extremely small relative to the amount of information that they carry, which means they're very easy to move around the network as caches deploy, as front ends reconnect to caches, and they're very efficient to search through. All right, so we've seen here how we can shard each one of these pieces and solve all of the fan-in and fan-out problems that we had from before. So the invalidators are only consuming from a single database shard. When they generate an invalidation, they know to route the cache key to only the cache node that is actually interested in it. So we don't have any fan-in at the cache nodes. And then the cache nodes know how to route invalidations only to the front ends that are actually interested in those queries using the probabilistic filters. And then when the front ends see that a query that they're interested in is invalidated, they just requery. So this helped us simplify greatly what LiveGraph's relationship with the database is. We just look at queries, we send them along when we need to. We never have to interpret them or mutate query results as changes come in. We just requery. All right, some conclusions. So LiveGraph can scale horizontally to keep up with Figma scale. As we're adding more users, we can add more machines. As we're adding more database machines, we add more invalidators. As we add more traffic, we can add more cache shards. And as we're adding users, adding clients, we can add more front ends. The mostly static query shapes and the three-tier architecture are what helped us to do that. And then third, sharing the cache, moving it out, centralizing it, gave us much better cache effectiveness. So we can get better performance at a higher cache hit rate for much lower cost. I want to talk a little bit about the future work that we're taking on following this project. So one of the big things is that we want to bring the same effortless real-time to server-side computation that we have for objects that are directly delivered out of the database. So we've mostly been talking about objects in the object graph that are selected just by database queries, but not all of them are that way. We have different amounts of server-side computation for different use cases. For example, you might have old clients that you want to maintain compatibility with. You're adding rich text to a field, and you need to be able to still deliver the plain text that those old clients are looking for. And we have several different features that do this of varying level of complexity and power, but the most powerful of them requires a bunch of handwritten stuff, just like the pre-LiveGraph days where we have pub subs to deliver invalidations back to LiveGraph. We have some ideas for how to do this really well so that we have the same effortless real-time with server-side computation involved. We need to improve our telemetry and developer experience. So it's really difficult to understand, with all the complexity that's happening inside of LiveGraph, what is happening when rendering UI and why. And so we want to improve our tools to help developers work better with LiveGraph. And then third, this new architecture helped open the door to increasing efficiency and lowering cost. So we have a few options on the table for further reducing cost of LiveGraph that we'll be exploring next year. Thank you so much for listening. And thank you so much to this wonderful, talented team of people. My information is here if you'd like to get in touch. And of course, Figma is hiring if this sounds interesting and you'd like to come work with us. Get in touch. Thank you.